For task 1, the growth of population in Uganda. We are mainly concerned with first-order differential equations for Uganda's population from 2001 to 2020. The application of the multi-region model used in task 1 is to find Uganda's population growth. Multi-region model assumes that the rate at which Uganda's overall population is growing at any given time. The multi-region model can be written as Pp over dt equal to Kp, where P of t is the number of populations in Uganda at time t years and k is a constant of proportionality. The objective of this task: use multi-region model to find total population in Uganda from 2001 to 2020 at any given year. To predict the future number of population in Uganda after 2020 using the multi-region model. To use the multi-region model to predict the past value of total population in Uganda before 2001, and to identify the reasons why the expected total population from 2001 to 2020 is not exact as recorded data.
Based on the data of population obtained from the World Bank Group, we can see that the trend of the population in Uganda is increasing from year to year. Thus, the differential equation method is used. To calculate the number of population in Uganda, we use the multi-region model, where the key idea is that the rate of change of the population is directly proportional to the population itself. Therefore, we get this equation where k is the constant of the proportionality. Next, we separate the variables into two different sides. Next, we integrate both sides, which leaves us with this equation. Next step is that we let a to be the plus minus exponential to the power of c, where the c is the constant of integration. Using the initial condition, which t is equal to 0, we substitute the value into the equation we got and solve for a, which gives us this value. Next, we find the value of k, where we substitute 2002 to be the t equals to 1 and the value of a into the equation. The particular solution now becomes this. Lastly, we calculate the estimated number of population from year 2001 to 2020 using the particular solution that we have obtained. The value can be seen in this table here.
The figure 1 on my left side is to show a graph of population in Uganda from the year 2001 and to 2020. Based on figure 1, the population of Uganda is the highest in 2020 with the population of 44,457,152. Corresponding with the graph, the population of Uganda is increasing with time. To predict a future record of the population in Uganda, we set t equals to 20, which represents the year 2021. As shown, the future record for 2021 that has been calculated is 46,277,264, while according to data.worldbank.org, the actual population in 2021 is 45,910,930. Therefore, we can observe that the estimated value is higher than the actual one. Next, to predict a past record of population in Uganda, we set t equals to -10, which represents the year 1991. After calculating it, the past record for 1991 is 18,095,274. Meanwhile, from data.worldbank.org, the actual value in 1991 is 18,155,901. Therefore, by comparing both of the values, we can say that the estimated value is smaller than the actual one. This figure 2 is a particular solution graph for Uganda's population from 2001 to 2020. According to figure 2, the graph of the particular solution for the population of Uganda is directly proportional with time. It is recorded that as time increases, the population of Uganda increases too. Therefore, we can predict that in the future, the number of population of Uganda would be higher compared to the years before. Next one is the figure 3, which shows graph comparison of actual and estimated population of Uganda from 2001 to 2020. Based on figure 3, we analyze that both actual and estimated graphs are increasing exponentially with time. Though by comparing both graphs, we can observe fluctuation from the actual values, which means there are errors present caused by several factors which will be explained further.
To calculate the percentage error, we use the actual and particular solution of future value. As seen in our calculation below, the values acquired by using the multi-region model are not accurate with the actual values. This error exists because real-world population dynamics are more complex than the simplified assumption of the Malthusian model. One of the factors that has affected population growth in the past is due to the high fertility rate in Uganda. Uganda's population has been growing at an alarming rate over the last few decades, making it one of Africa's largest and fastest growing countries. This is due to the cultural preferences for large families as well as the lack of access to family planning services in rural areas. Not only that, migration has been one of the key drivers of Uganda's population dynamics. Uganda's progressive refugee policies allow refugees the freedom of movement, right to work, access to healthcare and education. The policies have opened up the channels for refugees to integrate into Uganda's society, where they can contribute economically and to community development. Some of the items that could affect Uganda's population in the future are high birth rates, improved healthcare, and rural-urban migration. With healthcare services improving, infant mortality could reduce and consequently, population increase. Economic challenges, limited employment opportunities, and environmental pressures such as climate change could dictate migration patterns and population.
To apply this method, a formula is developed for calculating the area under the curves shaped like parabola. When rectangle and trapezoid are more suitable for linear functions, Simpson's rule provides a more accurate approximation for curve function. The formula for Simpson's approximate is given below.
For our assigned task, we have been given an equation to use the Simpson's rule. Figure 4 shows the tabulation of data for 6 subintervals using Excel. Firstly, we find the width by using the formula h equals to b minus a over n, where a equals to 0.2, b equals to 1.2, and n equals to 6. Therefore, our width is h equals to 1 over 6 or 0.16667. We can also find the value in Excel as follows. Next step is to find the value of x from the value of h we did earlier. Figure 4.2 shows calculation for values of x for 6 subintervals. Next, to find the value of fx, we substitute the values of x into the equation given. Same method is used to find other fx values by substituting the values of x respectively. Figure 4.3 shows calculation for values of fx for 6 subintervals. Next, we multiply the coefficients with the values of fx above. Below are the calculations to find one of the values. We do the same for the other values except for changing the column numbers. Figure 4.4 shows calculation of coefficients and values fx for 6 subintervals. To find the sum of the multiplication values we found earlier, add on all the values as follows. Figure 4.5 shows calculation to find the sum of multiplication of coefficient and values fx for 6 subintervals. And lastly, we find the integral of 6 subintervals as follows. Figure 4.6 calculation to find the integral of 6 subintervals. For B, the solving steps are similar to 6 subintervals except for the number of subintervals we are using for this part is 10 subintervals.
The actual value of an area is obtained by a graph on an online website which is Desmos. When there are 6 subintervals, the actual value of area is 0.815976 units square. From figure 7, we use 10 subintervals. The actual value of the area is 0.814511 units square. As we analyzed, we saw that the actual value of area for 6 subintervals is slightly higher than 10 subintervals. This is due to the fact that the higher the number of subintervals, the higher the accuracy of the area calculated. In conclusion, the objective of task 1 are fully accomplished as we understood how the first order differential equation were applied in our project. In task 1, we used the method to calculate the growth of the population in Uganda from 2001 to 2020. Next, we successfully managed to predict the future population of Uganda after 2020 using the Malthusian model. We were also able to predict the past value of the total population in Uganda before 2001. Then, by using the estimate number obtained from the model, we were able to calculate the percentage errors, which are the difference between the estimate population and the actual population. After that, we analyzed the possible reasons why the estimate population is not consistent with the actual data. Task 1 made us realize how useful the first order differential equation are because there are modern real world situations such as population growth and cooling of objects.
Furthermore, the objective of task 2 is also achieved, which is to find the value of integral of fx equal to negative 5x x cubed ln sin x squared from x equal to 0.2 to x equal to 1.2 for the 6 and 10 sub-interval. By applying the Simpson rules with the following step, we can conclude that the integral using the fixed sub-interval units of n equal to 6 and n equal to 10. We also identified the reason why the value obtained was different from the actual value.